Hello friends, this is all about equilibrium. Now what do you mean by equilibrium? If a body is subjected to all kinds of forces, to all kinds of moment, then essentially there will be a resultant of all these forces, and there would be a resultant to all this moment. And if the resultant of all these forces and the resultant of all this moment is equal to 0, then essentially we call this structure to be in equilibrium. What that means is, if there's a body like this, suppose, and it's subjected to F1, F2, F3 forces, and suppose there's a moment also M, and the resultant of F1, F2, F3 forces, suppose, is nothing but is equal to R. Right. Now if R vector is equal to 0 and this M vector is equal to 0, that essentially means that there are no resultant forces nor there are any resultant moments acting on this body. What it essentially means is then there won't be any acceleration, either translational acceleration or some kind of rotational acceleration within the body. And as such we can say that this will be moving with either a uniform velocity or will be at rest. And we know that civil engineering structures are mostly at rest. So essentially if a body is in equilibrium, we say that the resultant of all the forces, the resultant of all the moment will be equal to 0. Right. Now, what next? So therefore, we can say that if suppose that I have some kind of a body like this, and this are my support reaction, a hinge and suppose a roller, and this are my two forces acting, then if this is in equilibrium, if suppose that this body is in equilibrium, then what? Then what we have to do is basically we have to draw the free body diagram. Right. That is, we have to represent this body under the action of all the forces it is subjected to. Now this hinge will have two constraints basically. Number one, a constraint along the y direction, and let this be Ry1. A constraint along x direction, that is Rx1. And this will have a constraint along the y direction, that is Ry2. And these are the forces that this body will be subjected to. Right. Now from here, it's clear that if a body is in equilibrium, then essentially I have summation Fx must be equal to 0. That is, there won't be any resultant forces along x direction. Summation Fy will be equal to 0. There won't be any resultant forces along the y direction. And the moment about any point O must be equal to 0. That is, summation of moment about any point within the body is equal to 0. Now these three are called the three equations of equilibrium, and it directly comes from the fact that if this body is in equilibrium, I get these three equations of equilibrium. And here there are three unknowns basically, F1 and F2 unknown, Ry1, Rx1 and Ry2 are the unknowns. Rx1, Ry1, Ry2 are the three unknowns, or I should say the three constraints. Now, if the number of unknowns, let this unknowns be denoted as U, and the equations of equilibrium are denoted as EOE. If the number of unknowns is equal to the number of equations of equilibrium that we have, then essentially we can, just by solving these equations of equilibrium, we can solve these unknowns. So if EOE is equal to U, then it's a case of a statically determinate structure. And then we can say that the structure is statically determinate. If all the unknowns are found out basically by only the equations of equilibrium, then we say that the structure is statically determinate. If obviously the equations of equilibrium is less than the number of unknowns I have, then this structure is called a statically indeterminate structure. For example, I don't have a roller here. I have a hinge here, and therefore there will be another unknown here, Rx2. Right. Then essentially I will have four unknowns or four constraints and three equations of equilibrium. So just by solving these three equations of equilibrium, it's impossible to have the values of these four unknowns. We need additional equations of equilibrium that we call the compatibility equations that we'll study in the next lecture, and therein we can solve for these four unknown forces. So just by solving the equations of equilibrium, it's not possible for us to find all these unknowns. And essentially, if the number of equations of equilibrium is less than the number of unknowns, we have a case of statically indeterminate structure. Now, if I omit these two constraints and I say that this is free, then what? Then obviously the number of unknowns I have is Rx2 I will rub out and Ry2 I will rub out, and there will be two unknowns basically. Two unknowns, three equations of equilibrium, that is the equation of equilibrium is greater than the number of unknowns, then it will be an unstable structure. And we know that civil engineering structures are not unstable structures. So essentially, this thing, it's not of very important relevance, right? Just if we should know that if the number of equations of equilibrium is greater than the number of unknowns, we have unstable structure and we are not dealing with that, right? Now let us understand the significance of the statically determinate and statically indeterminate structure, right? Now in this case, there was suppose a hinge connection, and this was my Ry2 and Rx2. Then essentially, this was the case of a statically indeterminate structure. Now suppose this constraint no longer satisfies its function, that is, it allows translational motion, and therefore this Rx2 will be equal to 0. Then also we can maintain this body in equilibrium, as this Rx2 was just a redundant force, right? And this Ry1, Rx1 and Ry2 are enough. These three constraints are enough to keep this body in equilibrium. So essentially, if we have a statically indeterminate structure, we have some kind of redundant forces that we obtain basically. Redundant forces, right? And the number of redundant forces is basically equal to number of unknowns minus equations of equilibrium. Here the number of unknowns was 4, the number of equations of equilibrium was 3. So essentially I had one redundant forces which I could remove and still maintain this structure in equilibrium. But in case of a statically determinate structure, we just have enough unknowns as the number of equations of equilibrium. So if somehow one of the constraints do not satisfy its function, then essentially the statically determinate structure will be some sort of an unstable structure, right? So we have to, we should understand then what structure we should choose, a statically determinate one or a statically indeterminate one. Now the designers most often than not choose a statically indeterminate structure, because if at all the redundant forces no longer imposes its function, right, no longer satisfies its function, then also the structure will be in equilibrium. But in case of a statically determinate structure, if the redundant forces no longer satisfy its function, then it's gone. The structure is an unstable one. And that is all for this lecture. Thanks a lot for listening. Thank you.